Hello everyone, I Aditya Tiwari, Assistant Professor CSVTU Bhilai. In today's tutorial, we cover binary search tree. A binary search tree follows some order to arrange the elements. In a binary search tree, the value of left node must be smaller than the parent node and the value of right node must be greater than the parent node. The rule is applied recursively to the left and right subtree of the root. Let's understand the concept of binary search tree with an example. In the figure, we can observe that the root node is 40 and all the nodes of the left subtree are smaller than the root node 40 and the node of the right subtree are greater than the root node 40. Similarly, we can see the left child of root node is greater than its left child and smaller than its right child. So, it is also satisfies the property of binary search tree. Therefore, we can say that the tree in the image is a binary search tree. Suppose if we change the value of node 35 to 55 in the tree, check whether the tree will be binary search tree or not. In the tree, the value of the root node is 40, which is greater than its left child 30, but smaller than the right child of 30, it means 55. So, the tree does not satisfy the property of binary search tree. Therefore, the above tree is not a binary search tree. As per this case, we have to put all the smaller items at the left hand side of the root node, as well as we fix the all the greater items at the right subtree of the root node. So, the advantages of binary search tree are: searching an element in the binary search tree is easy, as we always have a hint that which subtree has the desired element. As compared to array and linked list, insertion and deletion operation are faster in binary search tree. We can understand by the example how we create a binary search tree. Now, let us see the creation of binary search tree using the example. We take some elements like 45, 15, 79, 90, 10, 55, 12, 20 and 50. First, we have to insert 45 into the tree. Initially, the tree is completely empty. The first element what we fetching, it will become a root node of that tree. So, here the first element is 45. 45 it will become a root node of the tree. Then we go for the next element. Then read the next element is 15. If it is smaller than the root node, insert it as the root of the left subtree and move to the next element. Otherwise, if the element is larger than the root node, then insert it the root of the right subtree. Now, let us see the process of creating the binary search tree using the given data element. The process of creating the binary search tree is shown in the diagram. First we insert 45, because we fetch the first element, that is a 45. Initially tree is empty, so 45 will become a root node of that tree. Now we fetch the second item is 15. When we fetch the second item, as 15 is smaller than the root node item 45, so insert it as the root node of the left subtree. In step 3, when we fetch the next element is 79. As 79 is greater than 45, each and every case when we fetch a new item, we compare with initially with root item, then we fix that item. So, as 79 is greater than 45, so insert it as the root node of the right subtree. Next element is 90. 90 is greater than 45 and 79. So, first we compare with the root node item, then we move to the right subtree, we follow the right subtree. Here we having an item is 79. Again we compare with the 79. 90 is greater than 79. So, it will be inserted as the right subtree of 79. Next element is 10. Again we compare with the root item. 10 is smaller than the 45 as well as 15 also. So, it will be inserted as a left subtree of 15. It means 10 will be a grandchild of 10. Next element is 55. 55 is larger than 45. First we compare with the root item and smaller than the current successor of root node, right successor of root node, that is 79. So, it will be inserted as the left subtree of 79. Next element is 12. 12 again comparing with the root item is 45, 12 is smaller than 45 as well as 12 is again smaller than the left successor of the root node, that is 15. So, it will be inserted as the right successor of 10. Next element is 20. 20 is smaller than 45, but greater than 15. So, it will be inserted as the right subtree of 50. Next element is 50, that is the last element. 50 is greater than 45, but smaller than the 79 and 55. So, it will be inserted as the left subtree of 55. Each and every case we have to cross check and compare the elements of the root node. If we follow the left successor, either we follow the right successor, we have to shift that way and we insert a new item. In that way we can create a binary search tree. By this tree you can understand how we inserted elements in a binary search tree. Now, the creation of binary search tree is completed. After that, let us move towards the operation that can be performed on binary search tree. We can perform insert, delete and search operation on the binary search tree. Let us understand how a search is performed on a binary search tree. Searching means to find or locate a specific elements or node in a data structure. In binary search tree, searching a node is easy because elements in binary search tree are stored in a specific order. These steps of searching a node in binary search tree are listed as follows. Number 1, first compare the elements to the searched with the root element of the tree. If root is matched with the target elements, then return the node's location. If it is not matched, then check whether the item is less than the root element. If it is smaller than the root element, then move to the left subtree. If the element is greater than the root element, then we move to the right subtree. If it is larger than the root element, then move to the right subtree. Repeat the above procedure recursively until the match is found. If element is not found or not present in the tree, then return null. If our pointer reach to the leaf node and when we do not found any searching elements in the tree, so we write the null value. It means the item is not available in the binary search tree. Now, let us understand the searching in a binary tree using an example. We are taking the same binary search tree formed in previous slide. Suppose we have to find node, or we can say item 20 from the below tree. Here we take a same example, 45 is a root node and all the items are fixed as it is the position what we created in the previous one. So, starting here our item is searching item is 20. So, again we are starting from the root node. So, we fix our pointer at the root node and compare the data with the item. Here the root node item is 45. So, we compare 20 with 45. By this comparison, we understand 20 should be connected at the left subtree of 45. So, we follow the path of the left subtree, we do not go the path for right subtree. So, the next left successor of 45 is 15. Compare with the left successor 15 and move to the right successor, because our searching element, our searching item is greater than the 15, it should be fixed at the right subtree of right successor of 15. In a step 3, right successor item is 20, here the data is also 20 and item is also 20, here our data will be matched. So, our search is successful. Here 20 is a grandchild of the 45. So, by this way you can search any element in a tree, binary search tree. Suppose here we search 50, the next searching item is 50. Again we compare with the root item 45. So, 50 is greater than 45. So, we go for the right subtree of the 45, we can't go for the left subtree. Here the right successor of 45 is 79, our item is fixed 50, 50 is less than 79. So, we go for the left subtree, not go for the right subtree. Here the left successor is 55, again we compare with the element, again we find out 50 is less than 55. So, we go for the left subtree. So, here when our pointer is moved to the 50, or we can say the left successor of 55, here the data is 50 and element is 50, both are matched, our operation is successful, search is successful. By this we can search any element or any node in a binary search tree. So, algorithm of binary search an element in a binary search tree, like search step 1, in a step 1 search root item. If item equal to root of data or root equal to null, then return root. If you find your searching item at the root item, so it will be search is successful. Do not compare with anyone and do not shift your pointer to any left subtree or right subtree. Either if tree is empty, so root equal to null. So, display the root or return the root. Else if item is less than data of root, return search your pointer to the left successor of the root. Else your pointer will be shifted to the right successor of the root. And if finally, we in a last step we exit the operation. So, this is the searching part, already we completed. Now, we move on the next operation, that is called a deletion in binary search tree. In a binary search tree, we must delete a node from the tree by keeping in mind that the property of binary search tree is not violated. To delete a node from binary search tree, there are the 3 possible situations occurs. First one, the node to be deleted is the leaf node, or the node to be deleted has only one child, and the node to be deleted has a 2 child. There are 3 type of situation when we go for when we performing a deleting operation. So, we will understand the situation listed in detail by the diagram. So, when the node to be deleted is the leaf node, it is the simplest case to delete a node in a binary search tree. Here we have to replace the leaf node with null and simply free the allocated space from the tree. We can see the process to delete a leaf node. Leaf node means this is the last element, that is the external node which don't produce any child, that is called a leaf node. We can see the process to delete a leaf node from binary search tree in the image. In image, suppose we have to delete node 90, as the node to be deleted is a leaf node. First you have to cross check your element, the deleted item, your deleting item will be a leaf node or not. Here 90 is a leaf node because 90 don't producing any child. So, it will be replaced with null and the allocated space will free. Before the deletion, you can see 90 will be connected at the right child of 79, or we can say 90 is a right grandchild of 45. So, after deletion we can easily remove our 90 from the tree and pass the null value at the tree. So, 90 will be disconnected and tree as it is. When the node to be delete has only one child, either a left child, either a right child. Only if we want to delete a node having only a single child. In this case, we have to replace the target node with its child and then delete the child node. It means that after replacing the target node with its child node, the child node will now contain the value to be deleted. So, we simply have to replace the child node with null and free up the allocated space. We can see the process of deleting a node with one child from binary search tree in the given image. In the given image, suppose we have to delete the item 79, or we can say the node 79. As the node to be deleted has only one child, so it will be replaced with its child 55. So, the replaced node 79 will now be a leaf node that can be easily deleted. So, before we deleting 79, the structure is this one. Now, after deletion of the 79, 79 should be replaced by the current successor child, that is only a single child, that is a 55. So, 79 will be deleted and 55 will replace 79 will replaced by 55. Rest item are as it is. Now, in the third case, when the node to be deleted has two children, that is a complicated case. In this case of deleting a node in binary search tree is a bit complex amongst other two cases. In such a case, the steps to be followed are listed as follows. First, find the in-order successor. In-order successor already we studied in a tree. In-order successor means in-order traversal. First we fetch the left item, left successor, then we fetch the root one, then we go for the right successor of root one. So, left, root, right, that is called a in-order traversal. So, we can follow the property of in-order traversal and find out the in-order successor of the node. So, first we find out the in-order successor of the node to be deleted. After that, replace the node with the in-order successor until the target node is placed at the leaf of tree, and at last replace the node with null and free up the allocated space. The in-order successor is required when the right child of the node is non-empty. We can obtain the in-order successor by finding the minimum element in the right child of the node. We can see the process of deleting a node with two children from binary search tree. in the given image. In the image, suppose we have to delete node 45. 45 is a root node and 45 having a both successor, left successor also and right successor also, and also having a grandchildren also. So, 45 that is the root node. As the node to be deleted has two children. So, it will replaced with its in order successor. So, before deleting we have to find out the in order traverse, by the in order traversal we have to find out the in order successor. Now, node 45 will be the leaf of the tree, so that it can be deleted easily. So, before the deletion 45 the structure is that one, and after deletion by the in order successor. So, the in order by the in order traversal we have an element like that 10, 15, 20, 45, 55 and 70. So, the current successor of 45 is 55. So, 45 should be replaced by the 55. So, after deletion of 45 the element replaced 45 by 55, the tree is root item is 55, left successor is 15, right successor is 79 and grandchild as it is. We easily remove the 45 from the given tree. So, after the second operation, the deletion operation, now we go for the insertion. How we insert a new element in a binary search tree? A new key in binary search tree is always inserted at the leaf. To insert an element in binary search tree, we have to start searching from the root node. If the node to be inserted is less than the root node, then search for an empty location in the left subtree, else search for the empty location in the right subtree, and insertion the data. Insert in binary search tree is smaller to searching, as we always have to maintain the rule that the left subtree is smaller than the root node and right subtree is larger than the root node. Now, let us see the process of inserting a node into a binary search tree using example. Here we having a tree like 45 is a root node, 15 is a left successor, 17 is a right successor, 10 is a left successor of 15, 20 is a right successor of 15 and 55 is a left successor of 79. Suppose I want to insert a new item that is called a 65. So, for again we start the comparing with the root item. 65 is greater than 45, it means we follow the right path of the 45. So, right successor of 45 is 79. Our new inserting item is 65. Here again we comparing with the right successor 79. 65 is less than 79. So, we follow the left path. Left path is left successor of 79 is 55. Again we compare with the left successor of 79 55 with the our new item 65. So, 65 is greater than 55. So, the right child of 55 is empty, it means 55 is a leaf node. So, 65 should be connected at the right subtree of the 55. So, by this you can understand how we connect a new element into a binary search tree. So, if you want to in this way you have to connect a 65. Suppose you want to connect a 100. Again we start with the comparing with the root item 45. 45, 100 is greater than 45, follow the right path. Next right successor of 45 is 79. Again we comparing 100 with the 79. Again 100 is greater than the 79. So, it should be connected at the right subtree, or we can follow the right sub path of 79. But 79 having a left subtree, but not a right subtree. So, we connected 100 at the right child of the 79 in a binary search tree. Suppose I want to connect 1. So, 1 is smaller than 45. So, we go for the left successor of 45, left successor is 15. Again we comparing the 15 with our item 1. 1 is smaller than 15, again we follow the left subtree of 15. So, again we next element is 10, 10 is a left successor of 15. So, again we comparing with the 10 and 1 is less than the 10. Again we compare, we follow the left path, but here 10 is a leaf node, not having a left child or not having a right child. So, 1 should be connected at the left of the 10. So, in this way we insert a new item in a given binary search tree. So, the complexity of the binary search tree. Let us see the time and space complexity of the binary search tree. We will see the time complexity for insertion, deletion and searching operation in best case, in average case and the worst case. So, the time complexity operations are insertions, deletion and searching. So, insertion having a best case means O log n, in average case O log n and the worst case O n. In a deletion O log n, again average case O of log n and the worst case is O of n. Here n is the number of elements, how many data are working in the tree. In a searching having a best case O of log n, average case O of log n and the worst case O of log n. So, where n is the number of nodes in the given tree. So, the space complexity are the same operation insertion, deletion and searching. In an insertion having a space complexity is O of n, deletion is O of n and search is O of n. The space complexity of all operation of binary search tree is O of n, that is complete depend on the number of items which we are using or performing inside the operations. So, here you understand the concept of how we calculate the time complexity and space complexity. If we working on the small amount of the data, at that time definitely the case of the all the cases are dependent on the number of data elements. So, the binary search tree, the application of binary search tree are when you working on the big amount of the data or we can say corpus amount of the data. At that time you using this kind of a structure or we can say binary search tree type of a structure. You can easily find out your elements in a tree. If you using, you can go for the linear type of data structure also for the inserting or deletion or same kind of operation in a data structure with the help of linear type of data structure, but it will take time. In a non-linear type of data structure in a tree, especially a binary search tree, we can easily find out, we can easily search or we can go for any operation in a smoothly way, like a searching operation, insertion operation and deletion operation. That is why all kind of operations what we are performing inside the binary search tree is quite easy and easy to locate that one, easy to remove any element, easy to insert element in a binary search tree. So, it is a best example. So, best topic to concept to understand how we insertion, deletion and searching an item in a binary search tree, because the space complexity of all the operations are same. So, basic problem in binary search, we have discussed all the advantages of binary search tree. The main drawback of binary search tree is that suppose when we creating a binary search tree and all the elements are in ascending order, and that would be design or creating a binary search tree. So, it should be first element should be become a root node, the next element should be connected at the right subchild of the right subtree of the root node, because the all data elements are the in ascending order. Suppose we take elements like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So, first element is 10, we fix that element as a root node, then next element is 20, 20 is greater than, again we compare with the root item 10, 20 should be connected at the right child of the 10, then next element is 30, 30 is greater than the root item 10 and as well as the right subchild, successor of 10 also 20, 30 should be connected the right successor of 20, like 40 will be connected as a right child of 30, then 50 will be connected as a right child of 40, 60 should be a right child of 50, 70 should be right child of 60, 80 should be a right child of 70 and 90 should be right child of 80 and the last element 100 is should be a right child of 90. It means we design a tree, but the problem is that we also with the time complexity are same, because the one ways process is going on. Left subtree is empty of the root node of any node, and all elements are connected at the right childs of the root node. So, same type of complexity, again the space and the time complexity are as it is, because in a linear type of data structure we follow the same operation, one by one we can move. In a tree also we can go for the same type of connection of the node. So, this is a drawback, or this is covered up by the AVL structure, what we cover in the next class. Thank you.